In this video, I'm going to discuss the second of the two extremely important theorems for integrations using substitutions. Like I mentioned in my previous video, while these theorems are not required to evaluate any integral, when you use those theorems, you can save plenty of time. Therefore, it's always important to know those theorems. So here is the second of the two theorems. Let's say you have to evaluate an integral of the form f prime x over fx dx, where f prime x is the first derivative of the function in the denominator, which is given as fx. In this case, your final answer will be equal to natural logarithm absolute value fx, and of course there will be a plus c. We will see how to prove this theorem. We will need a substitution as u equals fx. In that case, when you differentiate both sides, we know that you will get du equals f prime x dx. Then we can write down the given integral on the left hand side, f prime x over fx dx, as integration. In the bottom I have fx, which is equal to u. On the numerator I have f prime x times dx. F prime x times dx is actually equal to du. So this is equal to 1 over u du. We know that it's a result found in the standard table, which is natural logarithm u, and there will be a plus c. I need to replace this u with the original variable. Since u is equal to fx, the final answer is equal to natural logarithm absolute value fx plus c. That's the proof of this theorem. Now we will discuss two examples. Here's the first example. Let's say we need to evaluate the integral x cubed over 1 plus x to the fourth dx. As soon as you see this question, you can see that we can easily create the derivative of the denominator on the numerator. If you differentiate the function on the denominator, your answer should be 4x cubed. What I don't have in this question is just a 4, which can be created as 1/4 times integral 4x cubed over 1 plus x to the fourth dx. Now we can easily write down the final answer. 1/4 ln 1 plus x to the fourth, and there will be a plus c. That is because the denominator function, if we call it fx, it is 1 plus x to the fourth. If you differentiate that, you get this function right here, 4x cubed. And here in the final answer, I didn't use absolute sign with the natural logarithm. That is because for any value of x to the fourth will be positive, and that plus 1 will essentially be positive. Therefore, the absolute signs are not required for this final answer. Alright, we will discuss another example. So the second example is, let's say we need to evaluate the integral tan x. Well, we know that tangent x can be written as sine x over cosine x dx. If you differentiate cosine x, we know we get negative sine x. Since I don't have a negative symbol, I will write one negative symbol outside and another negative symbol inside. Now the two negatives will be cancelled and becomes positive. Now I can see that the function in the denominator cosine x, if I call it fx, I have its derivative f prime x as negative sine x on the numerator. Therefore, this theorem can be directly easily applied. There's this negative symbol. It should be ln the function in the denominator inside absolute signs, cosine x, and there will be a plus c as well. So this is one answer. Negative ln cosine x is one answer for the integration of tan x. We can simplify it some more and also obtain a second result, which is more prominently used as a solution for integration of tan x. If you remember the properties of logarithm, you know logarithm base a m raised to the rth power is equal to r times log base a m. That means if you have r right here, it can be written as m raised to the exponent. So I'm going to use that property and write down this negative as a -1, which is raised to ln cosine x term right here. So this can be written, there is a plus here as well, this can be written as ln absolute cosine x, this -1 I can write right here as an exponent, negative first power and plus c. What is cosine x raised to negative first power? It is equal to 1 over cosine x, which is actually equal to secant x. Therefore, this integral is also equal to positive ln absolute secant x plus c. So these two are standard results accepted as integrations of tan x dx. Alright, those two results were also obtained using this nice theorem without much work.